Welcome to Chapter 12 of University Physics. This is recorded for Aquinas Physics with Calculus class. We'll be going over static equilibrium and elasticity today. Two conceptually connected but mathematically divergent conversations. There's only 4 sections to this, but the first 2 sections are a lot of math. And again, I stress this every time. It's not math in the I'm introducing new things to you. It's math in the you need to take into account all the things we've talked previously and collect them all together. I go over certain problems, like the problems from the text. I, of course, skip over problems because I'm not going to go over every single problem in the textbook. But the problems I chose have a lot of stuff going on, but proper organization of your work and properly tracking back through the book will help you figure out and solve the problems in an efficient and timely manner. That's I say that all the time. As we get deeper into the book, that becomes more and more true. So as always, I go through the OpenStax provided PowerPoint slides. I reference back to the book. And yeah, let's begin. So when talking about static equilibrium elasticity, again, 2 separate sections. First things are equilibriums and then elasticity. Equilibrium essentially results in summing things to zero. We have stilt walkers in this position here. The stilt walkers are elevated above the ground, and yet they are not moving. There's no translational motion, which means no, straight or linear motion. And likewise, there's not really any torquing going on. There's lots of interactions, small interactions in the simple act of standing on these stilts as these two people are doing, but everything is balanced, and that balance, that summing to zero of all forces, be they translational or rotational, as we talked about in previous chapters, gives you the equilibrium that we're talking about here. These forces, of course, equal out because there's positive and negatives to descriptions of torque and translational motion. They are vectors, right? You put a little arrow above them when you draw them, or you bold them when you draw them for a reason. Clockwise, positive torque. Sorry, counterclockwise is positive torque, clockwise is negative torque, things along those lines. When you add up all the components of something that is not moving, you're not adding up nothing. You're adding up a bunch of positive negatives that combine to equal nothing. That's the fun trick of it all. And when we go through various examples, you're going to see how this stuff plays. We talked about center of gravity and center of mass conversations in previous chapters. That plays a big role here. We've all probably seen a large truck driving on the road, taking corners and not falling over, right? But if a truck takes that corner too fast, it will fall over if it's heavily loaded. These diagrams here, I think, do a pretty decent example of explaining this concept. Center of mass being within the axle space, as opposed to being outside the axle space, gives you that lean or that non-lean, that stability factor that we're talking about here. And the stuff is all mathematically derived too. In fact, there was a good center. Here we go, static equilibrium conditions. Basically, everything sums to zero, as I said. That's what we're going to be doing for the math of this chapter. There is a pretty good center of gravity calculation question here, 12.1, that I'm skipping over, but it's probably worth going through when you, after this lecture, when you watch it, because the book does a very good job. Keep saying that. The book does a very good job of walking through this stuff slowly. And what I love about the book is it links back with hyperlinks to the equations that it talks about. So when it skips work, it links you directly to the equation, so that way you can write the equation down and follow through the work yourself to figure out what's going on. Super useful stuff. Again, that's the picture for example 12.1. And here are some of the feedback diagrams that go through that example. Notice here that as stuff gets more complicated, it's more and more important to write things down in a way that makes sense. Give yourself plenty of paper to solve these problems, because drawing out free body diagrams is super useful. For example, the little r sub f equals d minus x over there, that's a determining factor that is drawn out from drawing a free body diagram. Are you dealing with x or d minus x? Is d, of course, being the distance from the center of mass to some point, right? And even screwing those two up will result in very different results, because you have a front and a rear of the car, and then where you put your distance d is going to dictate your answer. If you put that little r sub f behind the center of mass at the rear, you're going to get a different the d minus x. If you put that with the little r sub r instead of the little r sub f, you're going to get different results. Important to follow through and do proper paperwork with all these conversations. Instead of doing the center of mass calculation, we're going to do this one instead, which is 12.2. So let me scan over 12.2 and you can see some of this. But as I'm scrolling through here, right, a lot of work, and more importantly, a lot of text explaining the work. So 12.2, braking attention. A small pan with a mass of 42 grams, so remember SI units, is supported by two strings as shown in the picture. The maximum tension that the string can support is 2.8 newtons. So both those strings are made up of something that can hold 2.8 newtons of tension before snapping. Mass is added gradually to the pan until one of the strings snaps. Which string snaps, so the 5 centimeter, 10 centimeter, which string snaps, and how much mass is added for this to occur. So even though they're made of the same material, the fact that they're different angles and they're at different lengths plays a role in which one snaps first. And this is lots of applications in a real world setting, especially towards engineering applications. You can't always build things perfectly level, right? So what is our strategy here? Well, this mechanical system, of course, consists of strings, masses, and a pan in a static equilibrium. Static equilibrium means things are not moving translationally or rotationally. As we talked about at the beginning of this chapter, that means everything involved with this system sums to zero, right? Specifically, the knot that ties the string to the pan is in static equilibrium. The knot can be treated as a point, right? Therefore, we only need the first static equilibrium condition. So all the forces sum to zero. The three forces pulling at the knot are the tension of the 5 centimeter string, the tension of the second of the 10 centimeter string, and of course, gravity. Those are the three forces acting. We adopt a rectangular coordinate system, as usual, with the y-axis pointing opposite the direction of gravity, as usual, and draw a free body diagram, as shown here. There's a lot going on in this free body diagram, right? Because this free body diagram is both the three forces and the deconstruction x and y coordinates of said three forces. What I'm going to suggest you do when you draw out these sort of questions is draw second, draw third, draw fourth free body diagrams so you can separate them and you can follow the train of logic and not get confused as to what's going on, or draw different colors. That works too if you got colored pencils. To find the tensional components, we identify the directions of alpha 1 and alpha 2 that the string make with the horizontal direction. That is the x-axis. As you can see from the figure, the two strings make right triangles, right? We knew that. So we can use Pythagorean theorem to solve for them. Right triangles meaning we have, right, a triangle. So if you know parts of the triangle, you can solve for the parts. The entire triangle needs to sum to 180, right? We're talking trigonometry. We're talking high school math at this point. Then we can solve the tensions in the rectangular components, the x and y coordinates, right? Substituting the first condition of equilibrium and solve for the tension of the strings. The tension with the string of the greater tension will break first. Cool. So there's your Pythagorean theorem, and it's solving out sine and cosine of the parts there to be 1 over square root of 5 and 2 over square root of 5. Those are the x and y the 1 over square root of 5 and 2 over square root of 5 for the 5 and the 10 solve for the x and y components, right? We talked about this stuff, chapter 2? You're probably well familiar with everything eventually becomes a triangle in physics. So how do we solve this? Well, now that we have a good free body diagram of the situation, we have broken everything down to x and y components. Namely, in the x direction, you have the two tensions, or the two x components of the tension, and those sum to zero since the thing's not moving, it's in static equilibrium. In the y direction, you have the two strings pulling up and gravity pulling down, and again, everything sums correctly to zero. And then when we remember that everything's a triangle, we can substitute T1x and T2x, T1y, T2y for descriptors based solely on tension and that x and y component, which is what's giving us the T1 over square root of 5 or the 2T2 square root of 5 again, based off Pythagoras theorem. So we have everything, we have all the components of the static equilibrium in terms of purely x and y components, and we know that everything needs to sum up to zero. Fantastic. And notice when we do this, we also have masses involved, right? Because, as shown here, the y direction has that gravity component, which is the mass of the plate plus any additional mass you add to it to snap the string. Or as said here, the equilibrium equation x direction shows us the tension T1, the 5 centimeter string is twice the tension of T2, right? We have this 2 here for a reason. Therefore, the shorter string will snap. This is due in large part to the fact, of course, that the shorter string is also receiving more of the weight in its x component, right? Because it's in its y component because it's pulling straight down. So since we know the shorter string is the one that's going to snap, this 2T1 over square root of 5, that's what we think we need to solve for. At what point does that snap? Or, as this is, therefore the shorter string will snap. When we use the first equation to eliminate T2 from the second equation, we obtain a relationship between the mass of the pan and the tension of the string, which is shown here, right? So, when's the string break? The string breaks when the tension reaches its critical value of 2.8 newtons. We know that because we're told that the string breaks at 2.8 newtons, right? So, solve for what mass, unknown mass, I think little m, right? Yeah. Solve for what unknown mass, little m, results in T1 equal to 2.5. Plug and chug in. You get about 0.0277 kilograms or 277 grams. Meaning, when you add slightly over a quarter of a kilogram to this figure, the string will snap. There was a lot going on there, right? When you look at it at the base end, these ridiculous looking complicated diagrams and all these square roots going everywhere, it looks like a lot. I keep stressing this throughout this course because if there's any takeaway you get from this physics class, it's that I want you to be meticulous and I want you to write stuff down. When you write it down and you look at your free body diagram, oh, I got triangles there. Well, let's solve this triangle. Oh, cool. I know things in XY components. Can that play a factor? Well, if everything equals 0, then I can just set things to 0 and then solve for what I don't know. Oh, look, the tension on string 1 is twice the tension on string 2. Well, okay, move forward that way. These things can have not complicated solutions if you take the time to solve them. This basic concept applies to a lot of other things, of course, including here more examples of static equilibrium. I skipped over a few of the questions in section 2 because they're redundancies of the same concept. If this thing's at equilibrium and can you solve any one of the masses if you know the other two? Yes, you can. It's all about writing down your knowns, solving for your unknowns, right? Writing out free body diagrams to understand exactly what's going on. 12.4 is the example from this chapter that I chose. I chose this because I know, again, a lot of you are biology students, so I wanted to find a biology-related equation for that. Big problem-solving strategy with static equilibrium. These problem-solving strategy sections are cool. I haven't touched on them very much in the preceding chapters. They're cool, but they kind of tell you the thing I've been telling you over and over again. Write it down, write your equations, write your variables, write your free body diagrams, keep track of everything properly. That's how this game is played. So again, torque bands, I'm skipping over this, but feel free to go through it on your own if you want. It looks like a lot. but it's just keeping track of everything very well. So let's do 12.4, forces in the forearm. A weightlifter is holding a 50-pound weight, equivalent to 222.4 newtons, with his forearm, as shown in the figure. He's just holding it, so the weight's not moving, which means it's at some sort of static equilibrium. Being at static equilibrium means everything sums to 0. His forearm was positioned at some degree beta, which is 60 degrees with respect to his upper arm. So, right there, right? The forearm is supported by the contraction of the bicep muscle, which causes a torque around the elbow. That's how your arm works, right? Your bicep is what does your curls. Assuming that the tension in the bicep acts along the vertical direction given by gravity, what tension, it's just for simplicity's sake, what tension must the muscle exert to hold the forearm as the position shown? What's the force in the elbow joint? Assume we're not caring about the weight of the forearm for simplicity's sake, and give your answer in SI units. So a lot of stuff going on there. Notably here, the bicep is not attached at the focal point. It's attached, you're essentially having a shovel machine working here, right? Where you're picking up in front of the focal point, and then you're doing that to pick something up even further in front of the focal point. Your arm's basically a shovel, which is kind of cool. So how do we solve this? Well, we identify the forces, right? Told you that already. Identify your knowns and your unknowns, the unknown force on the elbow, the unknown tension of the muscle, and the known weight of whatever we're dealing with here. And adapt our frame of reference to set things into XY components, classically, of course, a Cartesian coordinate system. Draw out your free body diagram and figure out your X and Y components from the information you were given. Once you have those, sum everything up equal to 0. So this right here is our free body diagram, and we're going to take good point that we have F's, T's, and W's. What do those all represent? Well, W is classically weight, right? So that's doable. The X direction is along the forearm. That's interesting. Why do they do that? Well, read this section so you can understand exactly why they set the X-axis along the forearm and not just flat. There's saves you some math essentially. And the T is the tension of what? The bicep. Cool. And what is F? The fulcrum point. That's the point at where things move. So yeah, I'm not going to explain to you why they set the X-axis along the arm. I want you to read. If you don't know, if you get intuit it from the math, I want you to read and solve that problem. So when we see the free body diagram of the X component, we know that everything in the X direction solves to 0, and everything in the Y direction, of course, solves to 0. And basically the fulcrum and the tension of the bicep are both working against gravity to keep that static equilibrium. So we know this, and then again, this is what's real fun about this e-text, right? You can just click on the equations here to reference back to see why they changed things the way they did. Equation 12.21, 12.2 are two equations of the first equilibrium condition for forces. Next, we read the free body diagram for the net torque along the axis. So the torque is related to the fulcrum, right? To get that jazz for the second equilibrium equation of torques. All forces equal 0. All torques also need to equal 0 because the thing's not rotating. It's not moving translationally or linearly due to forces, and it's not rotating due to torques. So everything always equals 0. If you torque at your the torque given by the bicep moving up and the torque given by gravity pulling down, all of those things all equal 0. Can you solve what's up? The free body diagram shows that the lever arm is about 1.5 inches. As all the biceps are 1.5 inches away from the elbow, and then the weight itself is 13 inches away from the elbow, which is these guys here, right? So solving all that out, we can then, where we need to, draw triangles and solve X or Y components of what we're talking about. Since we, again, set the arm along the X-axis, let's solve out our triangles, which is what's done in this big stack of equations here. They're all very similar because they're all kind of at the same angle, right? 60 degrees. Substitute in the solved x and y coordinates for these equations, nets us these initially complicated looking equations, but all these equations is the solved x and y components from our initial 3-by diagram. And everything, of course, sums to 0. So when we simplify these equations, we see that we are left with really only 2 independent equations for the 2 unknown forces, F and T, the force and the torque, right? Because equation 12.1 for the x component is equivalent to equation 12.2 for the y component, you can essentially obtain the first equilibrium equation, which is your F plus your T minus your W, or your force plus your, right? Your force plus your tension, not torque, sorry, capital T is tension. Your force plus your tension minus your weight equals 0. And then, of course, your second equilibrium, your rotational forces are summed to 0. And then we simply plug and chug in our known equation to solve for what we don't have. Or we can solve for this tension here by substituting out what we know and what we don't know. We know, for example, the rotational weight. We solve for that. We solve for the rotation along the tension. So these guys here. Sorry, not the rotation, the radius, the little R's, right? I always get rotation and radius confused there. Sorry about that. We need better Greek letters, right? And they're pretty simple, actually, pretty kind of simple equations, right? The magnitude of the tension is about 433 pounds at what the muscle is imparting in there, and the force on the elbow is equal and opposite of that, right? So drawing a negative sign is simply an anti-parallel working direction, or it's the direction the force is happening upon. So when we multiply these things out and turn them into newtons, we land ourselves that the force is pushing downward with 1,705 newtons, but the tension in the muscle is upward of 1,927 newtons. So from all this information, there's 2 issues worth noting. The first concerns conversion to the SI unit, which is done at the very end of the solution in order to essentially not have to care about those things at the beginning, right? It kind of doesn't matter where you resolve your it doesn't matter where you resolve your units as long as you're consistent, right? The second important issue concerns the hinge joint at the elbow. In the initial analysis, the prime hinge joint should always be assumed to exert a force in an arbitrary direction. And then you must solve all the components of the hinge force independently, right? In this example, however, the elbow force happens to be vertical because the problem assumes the tension of the biceps to be vertical as well. That is part of the reason. I'm not going to give it away, but that relates to where we put the X direction, essentially. So we can adopt a different reference frame for this conversation. And you notice we do have slightly different looking equations there. However, I am not going to go over the same thing twice. If you would like to see what happens when we adopt a different reference frame, for example, not setting it along the arm, feel free to read the second part there. Pretty interesting stuff. It's pretty good math. Yeah, as I said, I think that's a very good example of what I've been saying throughout this entire chapter, which is the math looks hard, but it's if you follow your simple steps to keep tracking information, and you follow along with all your various Greek letters, they're easily solvable. The rest here, a couple more examples from the book, basically worked out problems along those same lines of where do you put all your variables. Very good to work through. I highly suggest going through these on your own to help you towards mastery of the subject. I'm not going to go through them for you, however. Sorry. All right, so to move on to the last section, we have a fun little conversation about stress, strain, and moduluses, or how things react to forces. There's Young's modulus, bulk modulus, and shear modulus. I think it's modulus, right? Yeah, it's modulus. Young's modulus, bulk modulus, and shear modulus. And these describe, in terms of pressure, pascals, how resilient something is to being changed. This is your elasticity, your plasticity conversation, which we'll expand a little bit upon in 12.4. Here we have in this chart here a good example explaining all these different things. Some things are better. Everything, let me back that thought up a little bit here. Everything has a strong axis and a weak axis to which to apply forces, right? Your bones in your body are a good example of this. Your arm bone is really good at taking force along the long part of the bone, right? You can hold a lot of force with your arms, but if you apply that same force to the center of your arm, you'll probably break your bone. Bones don't usually break long way. Bones usually break short way. That has a lot to do with the tensional and compressional strength, as shown here, of the bone. The fact that compression doesn't really have a, shear modulus and stuff like that. The math equation I chose for this is this example here, 12.7, and it is compressional strain. Essentially, what's shown in this picture here, how much do things shrink when you add weight to them? So here we have an example of a sculpture weighing about 10,000 newtons, resting on a horizontal surface, resting, static equilibrium, etc., etc., at the top of a 6 meter tall vertical pillar. So this heavy dude here on top of a 6 meter vertical pillar. The pillar's cross-sectional area is some 0.2 fifth of a meter squared. It's made up of granite with a mass density of 2,700 kilograms per meter. What is the compressive stress at the cross-section located 3 meters above the top of the pillar, and the value of the compressional stress on the top 3 meter section of said pillar? So halfway up, how much stress do we have, and what is the complete compressive strain along the top section of the pillar? So how much squishing is the statue doing, essentially, right? So first we find the weight of 3 meter long top of the pillar. This is important because the normal force acts on the cross section located 3 meters down is the sum of the pillar's weight and the sculpture's weight, right? Once we have the normal force, we can use equation from the text. They're shown here. Your perpendicular force divided by the area for your stress, and the change essentially in length over its original length for strain. And then to find these out, we need to use Young's modulus from the table that we saw initially. So this again is another example of figure out what the question's asking you, find your equations, plug and chug, right? The volume of the pillar and the cross-sectional volume of the pillar is given by the height of the cross-sectional area, of course. So the thing's 3 meters tall, has cross-sectional area of a fifth of a meter squared. We give us a volume of 0.6 cubic meters. Given some density, we can figure out therefore the weight of that top section of the pillar at 1.6 times 10 to the third kilograms, meaning the gravitational component of that is 1.568 times 10 to the fourth newtons of force being applied to that middle cross-sectional area. The weight of the sculpture is, of course, given us at 10,000 newtons. Sorry, 10,000 newtons. So the normal force of the cross-sectional surface area is given by the weight of the statue plus the weight of the structure, or 2.568 times 10 to the fourth newtons. So that middle section is having 25,000 newtons of force being put on it. So what is the stress in that situation? We'll divide that by its surface area. You get 128.4 kilopascals of pressure. Cool. That's a lot, right? Our strain, or how much the thing is moving, essentially, the compressive strain on that section is then therefore given to us by the amount of stress being applied to it times Young's modulus, or how much it resists that motion. The stronger the thing is, less likely it's going to change length and stuff like that. The larger the value of the stress modulus, in this case Young's, because of compression is what we're talking about there. And we land ourselves at a strain value of 2.85 times 10⁻⁶. Notice, of course, that the normal force acting on the cross-sectional area of the pillar is not constant along its length, right? It varies from the smallest value at the top to the largest value at the bottom because of how much pillar there is involved. Kind of obvious, right? There's going to be more pressure at the bottom of the pillar than the top because the bottom of the pillar has the rest of the pillar also applying pressure. We have very similar conversations and equations for the different types of stresses and strains. For example, when things bend, there's actually interplay going on between the different sources of the force when something bends, as shown here: tensile stress and compressive stress. Tensile stress wants to straighten out, compressive stress wants to push in. And those two play together to result in the forces of bending. This is why certain things will essentially break the way that they break, because of how they deal with various tensile and compressive strengths. You're going to notice, for example, when you bend a pencil and when you break a pencil by bending it, it always breaks from the top, right? It doesn't break from the bottom. There's a reason for that. Engineers understand this concept really well. I-beams have a specific shape to them. They're called I-beams for a reason, because that's a way to deal with the stresses, the massive stresses placed upon these construction equipment. Look it up sometimes. Engineering behind I-beams, it is fascinating stuff, and it kind of allows the world to exist at the heights, pun intended, that we reach. Bulk stress is the compressive nature of stress. This again has its own modulus components. That table we talked about here, I think bulk stress is, bulk modulus, obvious, right? And everything stress is definitely from that. Funny enough, it's not always the different materials will have different stress rates based on like the orientation of the molecules and stuff like that. Most things tend to have a larger Young's modulus than a bulk modulus, but that's not always the case. Example here, granite is the same, and copper actually is a lot better at resisting being squished from all directions than it is at reducing being squished from one direction. Right? Interesting stuff. And some things are very, very much stronger in one than the other. Nickel down here is a lot stronger in shear in Young's, or in that one direction that is in the bulk modulus. This concept is used a lot. The last chapter I cover for this is liquid tension, fluid statics, but how pistons work, and oh my gosh, what's his name? Not Archimedes' principle. I forgot the name of the principle. That's not good. The principle that allows like hydraulics to work follows this bulk modulus, bulk stress concept very well. It's really cool stuff, right? It's just the math behind reality is always more engaging than you thought it would be, and there's always a lot to this stuff. Go through the text, as I say every time, right? Go through text, do these examples. Right, here's the equation, the bulk stress equation for this piston, and see kind of how the math shows the reality that we live in. Shear modulus, of course, is the bending of something, or the shearing of it, the displacement of an object, pushing a desk, right? The desk will shove over a bit before it breaks. That's a shear modulus component. And this all, of course, ties into concepts of elasticity and plasticity. Elasticity is rubber banding. When you snap a rubber band, it comes back and looks the exact same, right? That's an elastic response to something. Plastic deformation is when it doesn't return to its original shape. When you have a soft plastic, you put your thumb in it and then your thumb print stays there, that's a plastic deformation. You've altered whatever you're dealing with in a way that it doesn't come back to its original shape. And fracturing is when something breaks. So there's a lot more to this conversation, but it does again revolve. It starts from the modulus variables of Young's bulk and shear and the material that you're talking about. So with that, I will end my presentation. The rest of this is unnecessary. And yeah, thanks for watching. And got any questions, shoot me an email, leave a comment. Take care.